In today's video, I'm going to explain about the atomic radii of the d block elements. We know that as we move from left to right across the period of the periodic table, then the nuclear charge increases because of the increase in atomic number, right? However, there are a few exceptions. Here we see that the atomic radii from chromium to copper do not differ much. Why is it so? Okay, I'm going to explain based on the electronic configuration. Here I'm writing only the valence shell electronic configuration for chromium up to copper. So the atomic number of chromium is 24, so the valence shell electronic configuration is 3d4 4s2, and then here 3d5 4s2, and so on. So look here, the atomic number from chromium to copper increases, right? So the nuclear charge increases. So because of that increase in nuclear charge, it pulls the 4s2 electron towards the nucleus. But we also see that as we move from chromium to copper, more electrons are added to the 3d orbital, right? So because of the addition of more electrons to the 3d orbitals, there is a screening effect. That means the screening effect increases. So that screening effect, it opposes the what? The attraction due to the nucleus. Suppose here we have an electron, okay? So let's say that here we have the 4s2 electron, and here we have the 3d. So the more the number of the electrons in the 3d orbital, the more will be the screening effect. And so this screening effect will oppose the attraction due to the nucleus. Okay, so because of that, the atomic radii from chromium to copper do not differ much. So you have to know that as the electron increases in the 3d orbital, then more will be the screening effect. So the more the screening effect, the more will be the opposition caused due to the screening effect. That means it opposes the attraction due to the nucleus. So that's why the atomic radii from chromium to copper do not differ much. They are very close to each other. We also have one interesting concept for the case of zinc, cadmium and silver. Now look here. From here, the atomic radii increases and then it starts decreasing in this way. Now here they are very close to each other, but then it suddenly increases for zinc, here also for cadmium and silver. Now how can we explain this? Again, we have to know the electronic configuration. So for zinc, the atomic number is 30, right? So what is the valence shell electronic configuration? It is 3d10 4s2. What about cadmium? It is 4d10 5s2. And then for silver, you can look the atomic number from the periodic table. For cadmium and silver, it is 5d10 6s2. Okay, look here. In these three elements, the electrons in the 3d orbital are more as compared to these, right? For the 3d series, here we have 10 electrons in the 3d orbital, which are more than in these other elements. So in that case, electron repulsion is greater in zinc, cadmium and silver. That means there will be greater repulsion among the electrons in the 3d orbital because there are more electrons. Okay, so because of this electron repulsion, there is an expansion in the electron cloud. So there will be an expansion, okay, expansion in the electron cloud. So because of that, the atomic size, okay, of zinc is greater. That is 1.25 angstrom. Here it is 1.48, 1.49, okay. Next, we come to this one. Now look at the 3D series and the 4D. Now the atomic radii of the elements in the 3D series and in the 4D series, their difference is very large. Okay, but then if we compare the atomic radii of the 4D series and the 5D series, the difference is very small. Look here, 1.62, 1.68, 1.45, 1.44. They do not differ much. Okay, they differ only by a small value. So why is it so? How can you explain that? That is because of the lanthanide contraction. Here we have lanthanum. Just have a look from the periodic table. See, we have the lanthanides, right? These are all the lanthanides. So in here, in these elements, there is a contraction known as lanthanide contraction. So because of lanthanide contraction, the atomic radii of the 4D series elements and the 5D series elements, okay, do not differ much. So as of now, just know that because of the lanthanide contraction, the atomic radii of the 4D series and the 5D series do not differ much. They are very close to each other, or they have almost the same size. Okay, so that's all about the atomic radii of the 3D series elements. Now we come to the most interesting question, the conceptual question based on this one. Atomic radius of copper is greater than that of chromium. Why? From the periodic table, it is expected that chromium should have smaller radius than that of chromium, right? But why is it that the atomic radius of copper is greater than that of chromium? That also we have to explain based on the electronic configuration. So look here. What is the atomic number of copper? It is 29. So the valence shell electronic configuration is 3D 9 4s 2. Okay, for chromium it is 24. So it is 3d4 4s 2. Or for copper we can also write like this: one electron jumps to the 3d orbital, so it will become 3d10 4s1. Here it will be 3d5. One electron jumps into the d orbital to attain the half stability state, right? And here also to attain the full stability state. So here will be 5 4s1. So look here. Here the electrons are paired, whereas here they are unpaired. So electron repulsion will be greater in copper. Okay, electron repulsion will be greater in copper than that in chromium. So because of that, there is an expansion in the electron cloud. So that's why atomic radius of copper is greater than that of chromium. Okay, so this is an interesting conceptual question. I hope you have understood about this one. That's all.